So this is our math now. We're asked to define the scenario, events, outcomes, and one possible final outcome. Someone help us out to start. What is the scenario in this word problem? Kelly, what is the scenario?
Khalid is trying to, is it Khalid?
Khalil.
Khalil is trying to pick out an outfit for the day.
Khalil's going to pick an outfit for the day. That is the context in which the things are happening. So we would say this is the scenario, right? Notice the scenario doesn't have a question. It's just part of a story. What are the events? First off, how many events are there? Two. And what are the events, Betsy? What? So that's the scenario you're trying to pick an outfit, right? The events are things that have to have outcomes. And they should theoretically have listed outcomes. So what are the things that he does? What are the actions that he takes that have different possible things that can happen? Julie? So he grabs a random shirt and a random pair of pants. These two things right here are the events. They are an action. Grabbing a shirt is an action. Now I get that picking out an outfit feels like an action, but there's no outcomes for that. It's not like we have a list of different outfits, right? So this event grabs a random shirt. What are the outcomes for that event? What are the different shirts that could be the result of grabbing a random shirt?
Plaid, checkered, black, and Hawaiian.
Plaid, checkered, black, and Hawaiian. So these four things, 1, 2, 3, 4, are the outcomes for grabbing a random shirt. One of the big ideas in counting problems is that events always must lead to outcomes. You can figure out something is an event if it has an associated outcome. And you can figure out if things are outcomes if they have associated events. They're paired intrinsically. Okay? So we have the 4 shirts as possible outcomes. What about pants? What are the outcomes for the pants?
Jeans, khakis, and sweats.
Jeans, khakis, and sweats. So we have this scenario. Let's try to figure out an outfit for the day. It has 2 events, grabbing a shirt and grabbing a pair of pants. He's not making a choice, actually. He's like, I'm just grabbing stuff. When he grabs a shirt, there are 4 possible outcomes. When he grabs a pair of pants, there are 3 possible outcomes. That's A, B, and C. What about D? What would be one possible final outcome? What would a final outcome be in the context of this scenario? An outfit. A shirt and pants. So what's one possible final outcome that you could have? Brittany? A checkered shirt. And what else? And jeans. Checkered shirt and jeans. That is one possible final outcome. What's another possible final outcome?
Hawaiian pants and khakis.
Hawaiian pants?
Oh no, Hawaiian and khakis. Sorry.
Hawaiian shirt and
Yeah.
khakis. That would be a nice outfit. Hawaiian shirt and sweats?
No, we don't know about that.
People have been like, apparently in another class, people are like, that is an old man outfit. But the point is it possible?
Yeah.
Yeah, it's possible. And so a lot of what counting has to do is determining questions like, how many possible final outcomes are there? Or, what are all the different possible outfits he could end up with?
12.
That is not the question. That is not the answer to what are the possible outfits.
Plaid jeans, plaid khakis, plaid sweats.
Okay? So today what we're going to look at is 2 different methods for how to figure out what are all the possible final outcomes of an event, or of a scenario with multiple events. Okay? Our goal for today is not to count them, it is to figure out what they are. And we're going to start by doing that with this actual scenario here. So I'm going to erase this stuff. We're going to look at the same scenario, and we're going to look at 2 different ways for generating these final outcomes. And I am already aware you're going to say, Paul, this is Math Extra, but I don't care. It's not Math Extra. I promise you, I'm a professional. Okay? Okay. So, close shirt thing I'm for the day. Boom. 4 different shirts, 3 different pants. The first method we're going to look at is what is called a list.
Yay.
We're going to generate a list of all the possible outfits. Okay? Now, when we wrote a possible outfit before, we wrote checkered shirt and jeans. I don't want to have to write every single letter for every single thing. So rather than writing out a list of words, I'm going to write a list of symbols. How do you think we can symbolize a plaid shirt? What could we use symbolically to represent a plaid shirt? We can use the letter P. So we're going to make a plaid shirt be the letter P, a checkered shirt be the letter C, a black shirt be the letter B, and a Hawaiian shirt be the letter H. And now we've saved a ton of time having to write all those full words. What do you think for jeans, khakis, and sweats?
JKS.
JK and S. So what we're doing now is we're saying, okay, we're going to symbolize these different possible outcomes with individual letters, and then we can list the outcomes in that way. Now this is where some students go in a bad direction. Did I hit start? Well, I just gotta make sure. Yeah, of course I hit start. I'm a professional, right? Because some students will just start being like, okay, plaid shirt and jeans, checkered shirt and khakis, black shirt and sweats, Hawaiian shirt and sweats, and they just start writing random stuff. Uh-oh, Brittany's already like, no sir. What's wrong with that, Brittany? Why is that not a good method? You can't understand it. Oh, you mean like they don't know what P stands for?
What is it for?
Oh, it's just like in a weird list? Yeah. Kelly?
It's just gonna get confusing because you don't know what you've listed already sometimes.
It's going to get confusing because you don't know what you've listed. And so I want to introduce a word and a concept, and one of the most important things, and one of the reasons why counting is a really great thing for students to engage in, and it's the word systematic. When we list, when we count, we want to be systematic. We want to have a process. We want to have like a method of counting so that it's less confusing and we don't miss things. My personal favorite way to be systematic in counting is to use alphabetical order. It is not a requirement. You can have other systems if you want. My preferred way to be systematic is alphabetical order. We have 4 pairs of shirts, P, C, B, and H. Of those 4 shirts, which is the first alphabetical?
B.
B. I'm going to start by finding all the black shirt combinations.
J.
Of the black shirts, he could wear jeans, khakis, or sweats.
J. Yeah.
J.
Oh,
J
okay.
is next,
It's
right?
in a-
So I'm going to list black shirt and jeans, black shirt and khakis, black shirt and sweats. I've written them in a column going down. They're grouped. You can go, oh, that's 3. What's the next shirt that we can choose from?
Checkered.
Checkered. I'm going to do the exact same thing. Checkered in jeans, checkered in khakis, checkered in sweats. I'm going to move on from checkered to, Hawaiian. Hawaiian and jeans, Hawaiian and khakis, Hawaiian and sweats. Finally, plaid and jeans, plaid and khakis, plaid and sweats. Notice how here we have like sweats as a row, khakis as a row. It's a really well organized, systematically derived list. How many events are there here? 2. When you have 2 events, it's not that hard to make a systematic list. When you have 3 or 4 events, when you have different kinds of counting problems, making a list can be a much more difficult thing. And so having a system in place is really, really important. This is called a list. It lists every possible final outcome. How many possible final outcomes are there?
12.
There's 12. It's a 3 by 4 grid. 3 times 4 is 12. How many of the outcomes have checkered or khakis? How many of the outcomes have checkered or khakis?
Checkered, 3 checkered.
So, well, let's checkered or khakis. 1, 2, 3, 4, 5, 6. Lists are incredibly useful because by having the entire list, we can answer more complicated questions than just how many. We're going to see tomorrow that there's a better way to answer how many, but lists are good for actually having outcomes. Okay? I feel like lists make a good bit of sense. So we're going to move on from lists. We're going to look at the other type of method, which is a little bit more extra, but will be a little bit more useful in some circumstances. Are there any questions about generating lists to count? Okay. Okay. So our first thing was a list. It generates like all the possible final outcomes symbolized. The next one we're going to look at is called a tree. A tree is also a method for generating all the possible final outcomes in these scenarios. But rather than writing them out as just letters, we're going to show them as like branches. So I'm going to demonstrate what I mean. We're starting here. This is him. This is the moment where he grabs a possible shirt. How many shirts were there that he could grab? 4. So we end up getting 4 branches from this point. Because this is a random point that has 4 different choices, we end up with 4 different branches. And the branches represent the exact same thing that they did in the list. So note this is called a branch. That's called a branch. Okay? So he could grab a black shirt, or a checkered shirt, or a Hawaiian shirt, or a plaid shirt. Every possible pathway is represented here. After he grabs a shirt, what is the next thing that he's going to do? Grab a pair of pants. How many pants were there to choose from?
3.
Each branch gets the future possible pathways. So here, if this was, what did we say? We said jeans, khakis, sweats, right? So this is jeans, khakis, and sweats. Jeans, khakis, and sweats. Jeans, khakis, and sweats. Jeans, khakis, and sweats. And this is called a tree diagram. How many final little endpoints do we have? 12. Which is the exact same number that we had when we made a list, which makes sense. It's a different method for creating the final outcomes. Trees can be cool because you can generate a list from trees very easily. Oh look, black jeans. This is black jeans, and black and khakis, and black and sweats, and here's your exact list generated from the trees. Okay? I know. You're thinking right now, this is so extra. I promise you, it's not. I promise you it's not. To do complicated counting questions, we have to have them be grounded in these things. This is what I'm doing my PhD research in, is the way that students make connections between lists of possible outcomes and the counting methods associated with them. Literally, I've spent more time thinking about it than anyone you'll ever meet in your life, unless you meet Elise Lockwood, who's a professor or Nick Wasserman, who's also a professor, and do this research. Unless you go hang out with them, I'm the top of you. I promise you, it's important for accounting, okay? So today we're gonna practice lists and practice trees. We're gonna look at examples of mistakes. We're gonna start trying to understand how to use them and when they can be used. Any questions from the class? There are these two methods. There are other possible methods that you could use. Lists and trees are, I think, the most useful. They cover the different kind of grounds. Now just to note, because we had two events here, we had two sets of branches. What if we had three events? What would happen?
You would add more branches.
You'd have another set of branches here. So I know that trees can get very cumbersome very quickly. We're not going to use trees for things that have 6 events, okay? But we need to understand how they work. Right, YouTube friends? Right.